The universe has multiple possible endings, and every single one of them is terrifying. From the cosmos freezing into eternal silence, to reality literally ripping itself apart, to a bubble of destruction expanding at light speed that you'd never see coming. Today I'm breaking down every major theory about how the universe dies, starting with the one scientists think is most likely: heat death. The most popular scientific theory for how the universe ends has one of the most misleading names in all of physics. Heat death sounds like the cosmos goes out in a blaze of glory, some massive thermal explosion that scorches everything out of existence. But it's the exact opposite. Heat death means the universe gets cold. Unimaginably, impossibly cold. The real killer isn't fire, it's boredom. Here's the thing, the second law of thermodynamics is the actual villain of this story. Entropy, the measure of disorder in a system, always increases over time. Energy spreads out, temperatures equalize, and eventually everything reaches the same lukewarm nothing. Lord Kelvin figured this out in the 1850s, and modern cosmology has spent 170 years confirming he was right. But the numbers get genuinely unhinged. Stars burn out around 10 to the 14th power years from now. That's 100 trillion years, and that's nothing. Black holes, the last meaningful structures in the universe, evaporate through Hawking radiation by about 10 to the 100th power years. That number has more zeros than atoms in the observable universe. After all of that, welcome to the dark era. A sparse, near absolute zero void filled with nothing but stray photons and electrons drifting so far apart they almost never interact. No stars, no planets, no light, just particles floating through infinite emptiness for eternity. Except maybe not eternity. There's a wildcard called the Poincare recurrence theorem, which suggests that over an incomprehensibly long timescale, quantum fluctuations could theoretically reassemble conditions for another Big Bang. The universe isn't dead, it's just waiting an absurd amount of time for the next roll of the dice. But if you think a slow fade into nothing sounds bleak, the next theory makes it somehow worse. Big freeze. So heat death is the thermodynamic verdict. The big freeze is what that verdict actually looks like happening. And it's somehow worse when you picture it. Stars burn out, galaxies drift apart. Dark energies, cosmological event horizon keep shrinking the observable universe until all that's left is the local group, our little neighborhood of gravitationally bound galaxies slowly going dark. The temperature drops asymptotically toward absolute zero. Every structure, every complex system, every process that could sustain life just stops. But here's where it gets genuinely unsettling. In 1979, physicist Freeman Dyson proposed something weirdly optimistic hiding inside all this bleakness. He argued that intelligent civilizations could achieve functional immortality by hibernating between increasingly smaller thoughts as the temperature drops. Since the minimum energy required for computation decreases as the universe cools, a civilization could theoretically stretch finite energy across infinite time, thinking slower and slower, but never fully stopping. It's a beautiful idea, a flicker of defiance against the cold, but dark energy killed it. The accelerating expansion creates an ever-shrinking event horizon that eventually cuts off all communication, all coordination, all the information exchange Dyson's scheme would require. The cold wins. And then comes the part that genuinely haunts cosmologists. Lawrence Krauss and Robert Scherer pointed out that civilizations living far enough in the future would look out at the sky and see nothing. Every galaxy beyond the local group will have receded past the observable horizon. The cosmic microwave background will have redshifted into undetectable wavelengths. There would be zero evidence that a Big Bang ever happened. These future beings would confidently conclude the universe is eternal, static, and empty. They'd be wrong about everything, and they'd have absolutely no way to know it. The universe doesn't just die. It erases the proof that it ever lived. There's even a variant called the long freeze, based on holographic dark energy models, where expansion decelerates asymptotically to a finite size rather than continuing forever. Different geometry, same cold ending. The details change, but the silence is identical. But if the big freeze sounds like the universe quietly fading to black, the next theory is the exact opposite. It's loud, it's violent, and it tears apart atoms. Big ripe. Heat death is slow. It's quiet. It takes trillions upon trillions of years to accomplish basically nothing. The Big Rip is the exact opposite. It's violent, it's fast, and it comes with a countdown. Here's the thing. The Big Rip requires something called phantom energy, a hypothetical form of dark energy that behaves in a way that shouldn't be physically possible. Normal dark energy has a constant density. As the universe expands, the energy stays the same per unit of space. Phantom energy actually gets denser as space expands. More space means more energy, means faster expansion, means more space. It's a feedback loop with no off switch. Whether this nightmare scenario can happen comes down to a single number. W, the equation of state parameter for dark energy. If W equals exactly -1, you get heat death. Boring, slow, inevitable. If W drops below -1, even by 1,000th of a point, you get the Big Rip. The current best measurement from the Planck satellite puts W at approximately -1.028 with an uncertainty of plus or minus 0.031. That margin of error is wide enough to include both -1 and values well below it. The difference between the universe fading out quietly and being torn apart at the atomic level is a measurement precision problem we haven't solved yet. But here's where it gets cinematic. If the Big Rip happens, physicists have calculated the exact sequence of destruction. Galaxy clusters get torn apart 60 billion years before the end. The Milky Way itself shreds apart 34 billion years out. 3 months before the final moment, our solar system is ripped apart, planets flung away from the sun as space between them expands faster than light. 30 minutes before the end, Earth disintegrates. And in the last 19 seconds, atoms themselves come apart. Electrons lose contact with their nuclei, then the nuclei dissolve, then spacetime itself ceases to exist. 200 billion years of escalating destruction, and it all ends in 19 seconds of atomic dissolution. And if phantom energy turns out to be stronger than current measurements suggest, say W equals -1.5, the Big Rip could arrive in just 22 billion years. The universe is only 13.8 billion years old. That's not some impossibly distant future. That's less than twice the age of everything that has ever existed. Nobody has ever detected phantom energy. Every observation remains consistent with W equaling exactly -1. But nobody can prove it equals exactly -1 either. And until someone can, the Big Rip stays on the table as a genuine possibility. But if the idea of the universe being ripped apart from the outside in sounds terrifying, the next scenario flips the script entirely. What if instead of expanding forever, the universe stopped, reversed, and crushed everything back into a single point? Big Crunch. So far, every scenario we've covered involves the universe expanding outward forever. The Big Crunch throws all of that out the window. This is the ending where gravity wins. Expansion slows, stops, and then the entire universe falls back inward, collapsing into a singularity identical to the one that started everything. Physics running the movie backwards. And honestly, it's the most intuitive ending there is. The universe exploded outward, so eventually gravity pulls it all back together, right? For decades, this was the leading theory. But here's where it gets complicated. For the Big Crunch to happen, you need either a closed universe geometry, meaning space curves back on itself like the surface of a sphere, or a negative cosmological constant, meaning the energy of empty space pulls things together instead of pushing them apart. The problem is that virtually every observation points in the opposite direction. The universe appears flat. The cosmological constant appears positive. Galaxies are flying apart faster and faster. In 1998, 2 independent teams studying distant supernovae discovered the universe's expansion wasn't slowing down. It was accelerating. That single discovery reshaped modern cosmology, earned a Nobel Prize, and essentially killed the Big Crunch overnight. For over 2 decades, it was treated as a relic. But here's the part nobody expected. In the mid-2020s, Cornell physicist Henry Tai reanalyzed data from major dark energy observatories and proposed something wild. The cosmological constant might actually be negative. If his analysis holds up, the universe reaches maximum expansion in roughly 11 billion years, then begins contracting, collapsing into a Big Crunch approximately 20 billion years from now. His work is contested, but Tai is a serious researcher at a serious institution, And the fact that this conversation is even happening again tells you how shaky our certainty really is. Now, the final moments of a big crunch would be nightmarish. As the universe contracts, the cosmic microwave background starts blue shifting. It climbs from microwaves to visible light, then ultraviolet, then X-rays, then gamma rays. The entire sky becomes a furnace. Atoms dissolve. Black holes merge. As space shrinks around them, everything, every particle, every photon, every scrap of matter that ever existed collapses back into a single infinitely dense point. The Big Crunch was dead for a quarter century. Now it's whispering from the grave. But if the Big Crunch sounds terrifying because you'd at least see it coming, the next scenario is worse. Because vacuum decay doesn't give you a warning. It doesn't give you anything. Vacuum decay. Every other scenario on this list gives you time. Centuries, billions of years, some incomprehensible number with 100 zeros after it. Vacuum decay doesn't. It could happen right now, this second, and you would experience exactly nothing. Not darkness, not pain, not a flash of light. Nothing. Because the bubble wall that destroys everything travels at the speed of light, which means information about its approach literally cannot outrun it. By the time it reaches you, you've already been gone for what might as well be an eternity. Here's the thing. The Higgs field, the quantum field responsible for giving particles their mass, might not be in its most stable state. Think of it like a ball resting in a shallow dip on the side of a hill. It looks stable. It feels stable. But it's not at the bottom. It's in what physicists call a metastable state, locally comfortable, but not the lowest possible energy configuration. And quantum mechanics has a nasty trick called quantum tunneling, which means the field doesn't need a push to fall to that lower state. It doesn't need a cosmic event, a collision, or a trigger. It just needs time. But here's where it gets genuinely unsettling. Theoretical estimates for how long our vacuum might last range from 10 to the 65th power years all the way up to 10 to the 500th power years. Those numbers sound comforting until you remember one brutal fact. The probability is not zero. And in a universe that lasts long enough, non-zero becomes inevitable. It's not a question of if. It's a question of where and when the first bubble nucleates. And this isn't purely theoretical anymore. In 2026, physicists at Tsinghua University built a tabletop experiment using a ring of ultra-cold atoms that actually demonstrated false vacuum decay in a controlled setting. They created synthetic false and true vacuum states, watched the decay happen in real time, and confirmed that the decay rate matched quantum field theory predictions almost exactly. First, direct experimental validation of the framework. The math works. The mechanism is real. But that's not even the part that should keep you up at night. A 2015 study found that black holes might dramatically accelerate the entire process. Black holes could act as nucleation seeds, vastly increasing the probability of a decay bubble forming nearby, which means the longer the universe exists, the more black holes form, the more nucleation sites accumulate, and the higher the odds climb. The universe doesn't just passively wait for vacuum decay. It actively builds the conditions that make it more likely. And somewhere beyond the edge of the observable universe, a bubble might already be expanding toward us right now. We'd never see it coming. But vacuum decay is only half the story. To really understand why this is so terrifying, you need to understand what a false vacuum actually is and why our entire reality might be built on one. False vacuum. Every scenario we've covered so far assumes the universe is playing by the right rules. But here's where it gets complicated, because the universe might not even be in the right state to begin with. The idea behind false vacuum isn't about what destroys the universe. It's about what the universe fundamentally is, and whether that foundation is real or temporary. In quantum field theory, the vacuum of space isn't empty. It sits at a specific energy level, like a ball resting in a valley. The problem is that valley might not be the lowest one. There could be an even deeper valley, a true vacuum, separated from us by nothing more than an energy barrier that quantum mechanics could tunnel through at any moment. And this isn't some fringe idea cooked up on a message board. The Higgs boson, discovered in 2012, has a mass of approximately 125 giga electron volts. That number matters enormously because it places our universe right on the knife's edge between a stable vacuum and a metastable one. If the Higgs mass were slightly different in either direction, physicists could say definitively whether we're safe or not. But at 125 giga-electron volts, the math refuses to give a clean answer. We're stuck in the most unsettling possible position. Too close to call. But here's the part that should genuinely unsettle you. A survey of physics experts, people who spend their entire careers studying this exact question, found that 45.6% of respondents believed our vacuum is metastable. Nearly half. Not a fringe minority. Not internet speculation. Nearly half of the people most qualified to answer this question think we might be sitting in the wrong energy state, stable only because nothing has pushed us over the edge, yet. And it gets worse. That same survey found 18.8% believe sufficiently advanced technology could artificially trigger vacuum decay. Almost 1 in 5 experts think a civilization could, in theory, end the laws of physics on purpose. The truly maddening part is that we cannot observe our way to certainty on this one. Unlike heat death or the Big Rip, where we can measure expansion rates and dark energy parameters, false vacuum exists in a category of scientific ideas that resist direct observation by definition. We can probe the Higgs field, we can refine measurements, we can check theoretical consistency. But we cannot look at our vacuum and confirm whether it's true or false because the only way to know for sure is if it decays. And by then, there's nothing left to observe. That's what makes false vacuum different from every other theory on this list. It's not a prediction about the distant future. It's a question about right now, about whether the ground beneath all of physics is solid or just convincingly stable. Every force strength, every particle mass, the speed of light itself, all of it could be artifacts of a vacuum state that isn't permanent. Inside a true vacuum bubble, those constants change. The laws of physics as we know them simply end. We're not waiting for the universe to break. We're asking whether it was ever fully built in the first place. But if the idea of a universe occupying the wrong energy state feels hopeless, the next theory offers something radically different. What if endings aren't endings at all, but transitions? Cyclic universe. What if the universe doesn't actually end? What if it just starts over? That's the core promise of cyclic cosmology, and it's the most philosophically comforting idea on this entire list. The Big Crunch doesn't have to be a finale. It could be a reset. The universe collapses, hits some extreme state, and explodes outward again in a brand new Big Bang. Our universe, in this model, isn't special. It's not the first, it's not the last. It's just one unremarkable chapter in an infinite book that nobody will ever finish reading. But here's where it gets complicated, because comforting and proven are two very different things. The most mathematically sophisticated version comes from Roger Penrose, a Nobel Prize-winning physicist who developed conformal cyclic cosmology. In Penrose's model, the universe doesn't bounce. It transitions. Each cosmic era, which he calls an aeon, begins with a Big Bang and expands until all matter decays and only radiation remains. At that point, the geometry of the dying universe becomes mathematically identical to a new Big Bang. One aeon's death becomes the next aeon's birth, seamlessly, infinitely. And Penrose claimed to have found evidence. His prediction was specific supermassive black holes from the previous eon should have evaporated through Hawking radiation, leaving anomalous hotspots in the cosmic microwave background. He called them Hawking points. In 2018, Penrose and his colleagues announced they detected these signatures at 99.98% confidence. A Nobel laureate claiming observational proof of a universe before our universe. But the story didn't end there. Independent researchers accounted for the look elsewhere effect, the statistical penalty you pay when searching an entire sky for patterns without specifying where to look first, and the confidence collapsed to roughly 87%. The scientific threshold for discovery is 99.99994%. Penrose's evidence went from groundbreaking to statistically unremarkable almost overnight. Even the best minds in physics can be undone by statistical noise. There's another version that sidesteps Penrose entirely. Loop quantum cosmology proposes that quantum gravity effects kick in at extreme densities, preventing the universe from reaching a true singularity. Instead of hitting an infinitely dense mathematical wall, the universe compresses to a minimum size and rebounds. No singularity, no breakdown of physics, just a bounce. But both models share the same devastating problem: entropy. The second law of thermodynamics says entropy always increases. Each cycle should inherit more disorder than the last. Yet every new Big Bang apparently starts in an extraordinarily low entropy state. How do you square infinite cycling with a law that demands ever-increasing chaos? Penrose's answer is that the conformal structure of spacetime renders entropy comparisons between aeons meaningless. Whether that's an elegant resolution or a convenient escape hatch depends entirely on who you ask, and nobody has settled that debate. The cyclic universe is beautiful. It promises that nothing truly ends, that destruction is always followed by creation. But, observationally, it's fragile. The best evidence fell apart under scrutiny, and the theoretical foundations still wrestle with thermodynamics. It's the cosmological equivalent of wanting something to be true so badly that you keep looking for proof, even when the universe keeps saying, "not yet." And if the idea of our universe being one cycle in an infinite chain feels overwhelming, wait until you consider the possibility that our universe is just one bubble in an infinite sea of them, each dying in its own unique way. Multiverse death scenarios. Every theory we've covered so far assumes one thing: that our universe is all there is. But what if it's not? What if our universe is just one bubble in an infinite foam of universes, constantly forming and popping across dimensions we can't even perceive? Because if that's true, then everything we just talked about, the heat death, the big rip, the big crunch, all of it becomes a local event. A single bubble popping in an ocean that never stops churning. This is where eternal inflation enters the picture. The theory predicts that the inflationary period that kickstarted our universe never actually stopped. It's still happening right now, somewhere beyond the edge of everything we can observe. Quantum fluctuations in the inflation field continuously spawn new bubble universes, each one with its own set of physical constants and laws. Some of those bubbles expand into something like ours, with stars and galaxies and atoms that behave the way we expect. Others collapse almost immediately, and others have physics so fundamentally alien that nothing we'd recognize as matter, energy, or even space can form inside them. But here's where it gets genuinely unsettling. Those bubble universes aren't necessarily far away in some abstract sense. They're neighbors. And if two bubbles with different physics collide, the result is something none of the other 7 theories on this list can predict. You'd get alien energy from a universe with completely different rules injecting itself into ours, potentially triggering an ending that doesn't have a name yet. The destruction wouldn't come from inside our universe. It would come from outside. Now, if you want the single strangest idea in this entire video, it's quantum immortality. Hugh Everett's many worlds interpretation of quantum mechanics says that every time a quantum event occurs, all possible outcomes actually happen, each one branching into its own separate universe. You reading this sentence right now? There's a branch where you clicked away 30 seconds ago. A branch where you never opened this video at all. And the wild extension of this idea is that consciousness always finds itself in the branch where it survives. You never experience the branches where you die. You just keep existing in increasingly improbable survival scenarios, branching and branching until the physics of your particular branch finally gives out entirely. It's philosophically bonkers, and physicists genuinely argue about whether it holds up, but nobody has definitively killed the idea. Now, before you assume the multiverse means anything goes and none of this matters, Stephen Hawking's late career work pushed back hard on that assumption. His no-boundary wave function models suggested the multiverse might be far smaller and more constrained than eternal inflation predicts. Fewer universes. A tighter range of possible physical laws. This would make the multiverse concept more predictive and potentially testable, rather than just an infinite playground of speculation. But it remains, honestly, the least empirically grounded idea on this entire list. We have zero direct evidence for other universes, the math works, the logic holds. but the proof isn't there yet. And honestly, that's the most remarkable part of all of this. Not the theories themselves, but the fact that they exist at all. Every single scenario we've covered in this video describes events that won't happen for billions or trillions or incomprehensible spans of years. None of it will affect anyone alive today, or anyone alive for generations beyond counting. And yet humans figured it out anyway. We pointed telescopes at 13.8 billion-year-old light, built mathematics that can describe the death of space-time itself, and asked the one question the universe never asked us to answer. What happens when all of this stops? We are the universe briefly becoming aware enough to wonder about its own ending. And whatever the answer turns out to be, the fact that something made of dead stars and old light managed to ask the question at all is more extraordinary than any of the answers. If you enjoyed this video and want to see more, click the video on the screen now,